Okay, well, welcome back. This section, we're going to talk about GIS, and I'm also going to talk about GPS and remote sensing technology, which are all integral parts. My voice is very raspy, so I'm going to be clearing my throat a lot. That's why I'm using the handheld so I can. Okay? Okay, so I'll give you some, we'll go over the basic concepts of geographic information systems, global positioning systems. I'm going to touch on remote sensing and show some examples of all of this stuff. Oh, and then we'll be talking about IRMA the last couple of slides, which is a NOAA product. It's the Common Operational Picture of Choice for a hospital. Okay, so let's just get basic. What is GIS? It's really computer hardware and software and people that know how to operate it and the data that's contained in it. It's a great data management tool. We have applications for collecting data in the field using handheld devices, remote sensing, and it's what's used to present situational display in a command post. And I'm obligated to put this slide up because invariably we are always inundated with requests that are not GIS. So I just want to list these for you. We're not IT support. That would be your logistics section. We don't make posters, make copies, print out files for you. Anything that's clerical in nature, that's what the documentation unit is for. And you'll see us sitting there with an array of printers and computers, but trust me, they're all in use for GIS. Okay, so how does GIS work? Well, on the simplest level, if you look at a map, you can break it down into 3 feature types: point data, line data, and areas. Okay? What's unique about a GIS, what takes it apart from a AAA roadmap, is that each feature is tied to a record in a database. Okay, once your data is in GIS, you can display it based on various attributes. These happen to be sample points in San Francisco for, I forget what for something or other. And that there relates to this record here. Yes, like I said, features are linked to a database record. And this gives you the ability to layer data on top, superimpose things, right? You don't see that happen because every feature is tied to the surface of the Earth. Okay, so why should we be there in the command post? We provide map products, that's pretty obvious. We can incorporate and manage all the various data that is collected during a response. We can quickly display and analyze the data. And because of its inherent data management capabilities, it makes GIS just a perfect tool for slow response. Okay, where do we fit in? Well, we're usually part of a situation. And this is from the August 2006 Homeland Security Incident Management Handbook. So we're kind of buried down there, and it looks like a very small part of the pie, but we actually provide service to a great portion of the response. And I could actually light up a lot more blocks there. Like I didn't even mention logistics, staging areas, things like that. Okay, so what kind of products or what kind of data are we tracking? SCAT data, degree of oiling along the shoreline. We're also tracking wildlife strandings, both oiled live and oiled dead. We'll track sampling locations and pretty much anything else that you're collecting out there that you can relate to the surface of the Earth. This is a SCAT map that was generated during the Costco Busan in San Francisco Bay. Hit the bridge right here. I know slide later, a close-up of Angel Island there from remote sensing. That'll show you real nicely. Okay, this is just zooming into that area. This goes back to the late 90s up in Humboldt Bay, where we were tracking dead bird locations and live oil bird locations. You can get a pretty good picture of where they will spread to based on this. Sample maps. This is from a pipeline break in Sassoon Marsh. Somebody was asking about wetlands, and we can use remote sensing. We did use remote sensing technology to compare this wetland to an area just north of here that wasn't affected. So what we did is we went and imaged right after the spill, and then we came back 6 weeks later and looked for change detection. I forget who asked that question, but that's one of the things we can do. And then here's a simple sign-off map. So we didn't have stats. Our scat segments were actually channels. And this is just somewhere along the progress of the spill here, where the heavy oil was still located, where they needed some more cleaning, and where it was actually signed off. We have various tools for data collection, handheld GPS, handheld computers. We are hoping to very shortly get into the tablet world. We use satellite-derived data and also airborne. This is one of our fishing game Argonavia observer aircraft. Okay, GPS. I'm going to get into a little GPS section here. Our pilots are in love with the older Garmin models. So GPS is basically satellite navigation. It's all weather. Doesn't matter if it's raining or nighttime or whatever. The simplest receiver you can buy these days will be accurate up to 15 meters, which is pretty good. That's, you know, pick yourself in an area the size of this room, essentially. Most receivers you buy these days can get actually better than that using this gloss. And even your cell phones can do better because they're tied into the cell tower, so another system of triangulation. And you need to be in touch with 4 satellites to get an accurate GPS location. 4, not 3. And I have a series of slides here that kind of demonstrate that. But first, this is just a cartoon of the American GPS satellite array that's up there. There's also a Russian array. And most receivers these days can get both of them. How does it work? Well, it's actually it calculates a distance based on time. Okay, so your GPS satellite is up there and it's essentially pinging, sending out a signal. The receiver on the ground picks up that signal and it knows how long it took for that signal to get from the satellite to the receiver. Okay, the next few slides will demonstrate that. But when you turn on a GPS, the first thing it does is it scans the sky, makes contact with the satellite, and downloads an almanac. So these satellites are in very precise orbits. So when the almanac is downloaded, the GPS receiver will know where all the satellites are in the sky, what's visible, what's not. Okay, so if your receiver is in contact with one satellite, right, that satellite is pinging in an omnidirectional, in all directions. So with one satellite, that receiver knows it's somewhere on the plane of this sphere. Doesn't know where, but it's a certain distance out from that satellite. You get 2 satellites, you're at the intersection of 2 spheres, which is a circle. 3 satellites, you have 2 points where they come together. 4 satellites, there's only one place where those spheres intersect, and that's your precise location. Okay, at OSPR, over the years, we've been working on ways to automate field data collection in order to get it from the field, processed, and then into the GIS as quickly and accurately as we can. For the last several years, we've been using a SCAD application that we purchased from Mr. Elaine LaMarche called Pocket SCAD. This is an older picture, but it runs on a handheld computer. That's a little Trimble Juno over there. You have base maps and then simple menus to fill out. It mimics all the boxes in the standard NOAA SCAD form. This is one application that we're hoping to migrate into the tablet world. Okay, so we used Pocket SCAD during the Dubai Star incident, right? And that was a fueling incident at Anchorage 9 in San Francisco Bay. The oil kind of spread out this way. We sent SCAD teams out, and this was all collected with Pocket SCAD. And you can see no oil, no oil, no oil. Pretty much it right in there. That would be it. Jordan, that's close to home. Is the other thing. Okay, we also use GPS in our resources at risk surveys, our pelagic transects that I showed you, that Parnavia aircraft. That's what they use. It's a plane that's designed to fly low and slow. The sides have windows that bulge out, so an observer can actually look down. But they have standard protocols that they follow when they're making their observations, and we get their track lines and their individual observations. These are species that they see along the way. Now, once this data is in the GPS and the GIS, we can display it many different ways. So here's an example. We're just showing abundance, total numbers of, these are not only birds, but they could be mammals too. So this is not species, just how many we're seeing. This is probably from that platform A spill. Not the 1969 platform A spill, the one that was 4 or 5 years ago. Okay, so for remote sensing, I'm going to just go over a tiny little bit of physics here. Okay, this is the electromagnetic spectrum. These numbers are very small. Gamma rays, they're so small they'll pass right through your body. These numbers are larger, very large, and those are radio waves. For oil spill response, we're operating in the visible, the ultraviolet, and the infrared. And remember, the visible can be broken up too into violet, indigo, blue, green, yellow, orange, red. So that's what we call a multispectral system, where we're actually looking at these different bands. Okay, I'm shooting over the Deepwater Horizon. There was a lot of remote sensing technology in play there. And these were the systems that were most effective for response purposes. So we had satellite radar, and I'll show some examples of this, both the Canadian and European satellites, and these operate in the microwave area. Visible light satellites, so optical satellites as we call them, the Lotus satellites that NASA operates. And then airborne. The Canadian, Transport Canada has an excellent system. It's called a SLAR, side-looking airborne radar. Very similar to the satellite synthetic aperture radar. The differences we're not going to talk about here. And also the Icelandic Coast Guard came in to relieve the Canadians when they were down for maintenance. And then we used a system that was developed here in California by Ocean Imaging, which is an airborne multispectral. And they're operating in the visible and the thermal. Okay, so this is an image from the Lotus Sensor at the early stages of the Gulf spill. So this here is the slick. You can get a pretty good picture of the size, but what you can't get there is the thickness variations within the slick. Okay, that could, a lot of that was just really sheet, which, as you know, you cannot collect sheet. But there were, it's well known, heavy pockets of oil there. An interesting feature of this image is you see all this is the Mississippi River right here. And there were some pretty big storms up north. So this river was flowing very high, and it actually kept the oil offshore for the first few weeks of the spill, give people time to react. This is a radar image of probably the same day, or very similar. Again, you get a good picture of the outline, the footprint, but you really don't know what's happening thickness-wise in there. So that could be a very scary looking picture, where in reality, there's just isolated pockets of very thick oil. Okay, I'm going to show a couple of images here to show the difference between radar and an optical satellite. Radar, as I said, is microwaves. It penetrates cloud cover. It's as if the clouds were not even there. And because the radar satellite provides its own source of illumination, rather than measuring reflected sunlight, it's independent of time of day. This could be midnight right now. So we're looking at Golden Gate right here. This is the traffic separation scheme. There's a few vessels here, Farallon Islands. So this, just note the time, 6 in the morning, this image was acquired. This is an optical image several hours later. So we're looking at total cloud cover here. Yet the radar has the ability to penetrate that. So radar is a great tool for reconnaissance, but you need other systems to measure thickness and actually verify the existence of oil. And I'll talk about that here. Okay, because it's so difficult to actually point your finger and say that is oil on a radar image, we realized we needed a system that could positively identify oil on the water. And the reason it's so difficult on radar because there's lots of natural phenomena that can mimic the appearance of oil on water. Silt, kelp beds, rain cells, dead cotton, all looks the same on a radar image. So we went with, we actually had a research project. Ocean Imaging had this multispectral camera that they had been using for kelp mapping along the coast of California. So we knew that we could positively pick out kelp from oil, and we did a series of overflights over the Santa Barbara Channel Sea. So we immediately saw, we could tell sediment and kelp from oil. And what we also found out is sunlight could be a real issue. So flying the system at high noon is not a real good idea. Somewhere along the line, MMS, now BSEE, jumped on board and provided funding and the OMSET test tank. So we made many trips to OMSET, testing the camera and modifying the algorithms in all different types of conditions. We did daytime imaging, nighttime imaging, cold weather, warm weather, calm water, and they have a wave generator in the back, big waves too. This is the original system sitting in a crow's nest over the OMSET test tank. That's how we did the imaging. Right? We filled up these targets here with a known amount of oil, so we had an area, a thickness, or an area and volume, and we could predict the thickness. And then we added the thermal camera too. Okay, so this was the Costco Busan oil spill. At the time, the system was not fully operational. We were sort of still in experimental mode, but we had an opportunity to fly, and we took it. And what you can see here is the blue color, the cyan, is sheen, and the red blobs here are essentially recoverable oil. And we even have some emulsions in here. I think there's some emulsion in that way. But if you look carefully, you can see all the cleanup vessels, and they're pretty much over here. You can actually see them towing their boom array. And it's not that they weren't collecting oil, because if you look closely, there is oil they weren't seeing a whole lot. And that's because, I mean, they have helicopter spotters, and they're probably going up about 500 feet, maybe 1,000 feet. And it's difficult to see, depending on for a lot of reasons. Here, we're flying at 10,000 feet, so we get, you know, a broader picture. And then these sensors, this particular sensor can positively identify all. This technology, by the way, is now available through MSRC. They went ahead and purchased 3 of these systems, and they're staging them on the East Coast, Gulf Coast, and here in California, I think it'll be in Long Beach. Okay, getting back to that thickness thing. This is from the Macondo blowout. This was I showed you that radar image, several slides. So this is the outline that was of the slick as seen on the radar image. This here was some of the overflight data from the ocean imaging system, and what it's showing here is the thickness values that you weren't seeing in the radar. So there was a lot of thickness variation. Again, this is sheen, thick oil is in red. Okay, now jump to the common operational picture. How am I doing on time? Have I got plenty? Okay, so the big thing in hospital response these days is the common operational picture. Everybody's got one. We prefer the NOAA product. This is actually the EPA, right? Geoplatform. There's my EPA guy there.
This is actually Geoplatform. This is the public side of
okay.
So it's like a EROS sensor.
Okay, so what is a COP, as we refer to it, a COP? It's a visual display of situational awareness. It will be based in the situation unit. It should be the sole source of response situational awareness. I mean, if you need to know what's happening in a spill, you need to be looking at the common operational picture that's in the incident command post. So IRMA, as I mentioned, is the COP of choice for California, developed by NOAA, ORNR, and the University of New Hampshire. That's where the programmers live. It was specifically designed as an OSPR response tool. There's a lot of vendors out there that are selling all event COPs. This one, IRMA, is specifically for oil spills. It doesn't mean it can't be used for other things, but it was designed with oil spills in mind. We've also determined that as an excellent planning tool for spill response. So OSPR GIS, and there's 2 of them in this room here, Greg White and Guffey, and Greg Huey back in Sacramento, and Melinda D. Herrera Rogers before she left us, and Isaac Oshima before he left, spent a lot of time getting all of the data out of the area contingency plans and into IRMA. So you can go into IRMA, you can look at all the sensitive sites, you can pick there's hot links that'll take you to the ACD page, all the ESI data, operational divisions, stats segments, that's all in Southwest IRMA these days. I encourage you all to look at it. I probably have the web address here, but if you do a Google search on Southwest IRMA, it should pop up. Okay, and it provides interactive map display capabilities to responders at your desktop or your tablet or your phone if you want to look at a little tiny screen. So it's web-based, there's no proprietary software needed for the use. And NOAA has input several layers of access. Okay, so there'll always be a public IRMA, which PIOs may find handy for briefings. And then there's responder level, where you're going to see stuff that the public's not going to see, okay? And that's, again, that's based on your credentials, which will be issued by NOAA, and they control that. Well, we've had some trainings, but in your book there, I actually included an exercise. If you look past the slideshow, there's kind of an IRMA primer in there. Okay, if you follow along that, using public IRMA, all right, you don't need credentials, you should be able to get a lot of information. How to get the ACP stuff, the ESI, and all that. Input coordinates to get to a location. It'll do a lot of things. So just briefly, here's the table of contents. You can change the background from standard map to satellite image, all kinds of political boundaries. The stuff that you would be interested in is under here under response planning, right? And it's all there. Most of it's there. When you see these little lightning bolts, those are hotlinks. So for instance, if you click on one of these sensitive sites, if you click on that, there should be 2 hotlinks for each sensitive site. One will get you to the ACP page, the ACP document with all the information on both sides. The other one will get you to an air photo of the site, a recent air photo that was collected by that California coastal project. And those are very recent, within the last one. Okay, here's an example of how we used IRMA at a small spill that we had north of here. I think it's Ventura Harbor. Yeah, Channel Islands, Ventura. So this red polygon here, that's what we call areas in the GIS world. They're called polygons. That's the area that was closed to fishing, and Lori worked on that. Lori and Greg here. The dots and squares are probably sampling locations. And then we can actually embed photographs too. These are actual field photos from in here. We can get into IRMA. So yeah, so you can send people out into the field, they can snap pictures, and we have the ability to post those right into IRMA. Thanks to Mr. Green White. Okay, so does IRMA have to be the COP? Well, we would prefer it, but no, it doesn't. As long as your data is collected and processed into GIS format, it should be able to go into anybody's COP. Okay? This happens to be the response group. This is their COP that they had built for the Deepwater Horizon, which, by the way, sort of became a problem because there was the official COP deemed by the Coast Guard to be IRMA, and then there was the RP COP where they were putting their data, and it got very confusing at times because they didn't have the same data set in each COP. So either you didn't know where to look or you didn't even know that the data existed. That's why in California here, we would like to see one COP in the command post. Okay, and if we have a data sharing agreement, which is integral to this now, then everybody has access to the data, and if Chevron wants to use a COP, their COP, for their use and their headquarters, that's fine. They'll be getting the same data sets that IRMA has, or whatever the official COP is. But that's the key, and that's something we're trying to play out here in California, what we call a cooperative GIS unit, where all the trustees and all the RPs, people, and vendors all sit at the same table, work in a common place, store the data, all the data in a common area, and through these data sharing agreements, everybody has access, either at the end of the day or at the end of the event. Everybody walks away with a CD or a DVD of the data set, so that we don't have this conflict anymore. Well, who's got this data? Well, it's over there. We can't get to it. It just makes for confusion and frustration, and those are two things you don't need in an oil spill because you're already confused and frustrated. Okay, so I answered all those questions. I think I got to this. Okay, one in the command post, one COP, and then you are all welcome to use your individual COPs for in-house use. And again, key to this is these data sharing agreements. So there are, in May here, there are actually 2 prep drills in California in May. One is Sector San Diego and one is Sector LA, LB. We're going to put this cooperative GIS unit into play there. So all the GIS people will be located in situation. There's going to be an assistant situation unit leader whose sole purpose is GIS coordination. We'll have everybody sign off on these data sharing agreements, and we'll see how it goes. For the San Diego prep, TRG will be running the CLP, and for the LALB prep drill later in May, NOAA will be running IRMA for that drill, and we'll see. Yes, we don't want competing CLPs, that's bad. Okay, and this slide just kind of shows my idealized conception of how the flow of data should occur. So in this data management oval here, this is where the cooperative GIS unit and situation unit sit, and they are tied to the hip, right? Because all data from the field is coming into situation, it's going to GIS for processing and archiving, then it's handed off to the common operational picture team for display purposes. And that's where responders and unified command, everybody will get their data from the CLP. Okay, one common source of data in the command post. I can't say it without time. So. That's it.